Good. So today is November 8, 2023, and we are right here. We are going to cover a little bit. In the first hour, we're going to continue covering chapter 7, and then we start with lab number 5. So here you go. Don't forget reports for labs 3 and 4 are due now. We'll cover chapter 7 during the first hour of class. After that, we will do lab 5. Okay, so let's just quickly review what we did before. Linear momentum, okay? Linear momentum. Linear momentum is important because if the net force applied to a system is 0, then linear momentum E equal to mv is conserved. Every time that you have conservation of a quantity, it becomes very easy to solve a problem mathematically. And that's why we study momentum under certain circumstances, okay? Under certain circumstances, it is possible to realize that the net force of a system, remember, is 0. Like in the case of two objects colliding, right? So examples, okay? Examples of conservation of momentum. 1, a single object moving over a frictionless surface. In this case, net force is 0. A single object moving over frictionless, in this case, net force is 0. And the velocity is constant. So the initial momentum is equal to the final momentum. Okay. This is the obvious case, final momentum. This is the obvious case.
Professor, sorry to interrupt. Are you sharing your screen?
Okay, thank you for letting me know. Here you go. Oh, here you go. I'll give you some time for you to digest that. Sometimes I get so concentrated on the text here, I stop checking my chat messages. So feel free to interrupt me and let me know, okay? So here you go. That's Wednesday. Reports for lab 3 and 4 are due. We'll cover chapter 7 during the first hour of class. After that, we'll do lab 5. Linear momentum. Linear momentum is important because if the net force applied to a system is 0, then linear momentum is conserved. By conserved, I mean P initial must be equal to P final. I'm not going to put the subscript there. Under certain circumstances, it's possible to realize that the net force of a system is zero. Like the case of two objects collide, like in the case of two objects colliding, or a single object moving with constant velocity, right? Or a single object moving in a straight line with constant velocity. Example of conservation of momentum, single object moving over frictionless surface, right? This is the obvious case. And then we have the not so obvious case, the not so obvious case. A system of two objects which are colliding. The momentum, the linear momentum, is conserved just before the collision at a t, is conserved at a t, at t, instant of time t, just before the collision. And I'm going to put t equal to 0 just before the collision. And at a, I'm going to put, let's see. Yeah, just before the collision, and at a t just after the collision. I can illustrate that very easily for you. Okay, so here you go. That's the nice thing of physics that allows you to choose the system itself. Okay, so if you go ahead and choose the system, the two masses, okay? This is a frictionless surface to make things easier. And also to make things even easier, the two masses have the same, these two objects have the same value, the same mass value. One is at rest, the other is moving. This object, one is moving towards the second one. It's about to collide with the second one. And then what's going to happen? Don't forget, I'm using these two masses as my system. I'm treating these two masses as though it were a single one. It's a single mass that's stretched and compressed, okay? But it is still a single mass, single object, can be considered a single object. At the moment of collision, object one applies a force to the right of on object two, and object two applies a force to the left on object one. Because these two masses are being treated as a single object, the net force in this system is going to be zero, because this force here plus this force here are going to be zero. Okay? That's a situation that's not so obvious. Imagine, how long it took for someone to figure that out. Okay, so after the collision, the two sets of masses move to the right. Okay, that's why we can say, from this instant all the way down to this instant, the net force applied to the object is zero. And isn't that nice? So, and this is the case of inelastic collision. The inelastic collision, because the two objects stick to each other. They don't bounce off each other. That's the simplest type of problem that you're going to see in collisions. One-dimensional inelastic collision with two masses, two objects having the same mass. Okay, and I'm going to document that here in my notes. Okay? In this case, we have the following situation. Now, this is the not so obvious case, a system of two objects which are colliding. The momentum is conserved just before the collision and a t just after the collision. Okay, and a t just after the collision. Why is that? Because the net force in this system must be zero. In other words, object one is exerting, let's see, is interacting, right? Interacting with object two, okay? With a force applying a force of F12, force of one applied to two. Conversely, object, let's put it in a different way. The not so obvious case, a system of two objects which are colliding. In this case, the momentum is conserved at t equal to 0 just before the collision and at t just after the collision. Okay? Momentum, let's see, is conserved for the following reasons. One, during the collision, object one is interacting with object two. Okay, in other words, object one is applying a force F1 in 2 to object 2. Conversely, and according to Newton's third law of motion, and according to Newton's, okay, during the collision of object 2. More specifically, one, object one apply force. C. Conversely, and according to Newton's third law of motion, object two must apply conversely, must apply a force F of 2 in 1, okay? Force of 2 applied to 1. Which is equal to minus F of 1 in 2, okay? Consequently, the net force acting in the system F21 plus F12, right, must be 0. Because of Newton's third law. Okay? This is not an obvious once you look at that for the first time, right? Remember, here you go. here in this system, we have only those two forces. Okay. Of course, we have the normal and the weight, but the normal and the weight cancels out, right? Now, the net force in the system is going to be F12 plus F21. But according to Newton's third law, F21 is minus F12. Okay? And I'm going to do like that. F minus F21. Okay? And now that we figured that out, we can start, and now that we realize that, and now that we have realized that, we can apply this knowledge to different situations. The first one is the easiest one. First one, two objects of same mass undergoing a totally inelastic collision. Okay? In the case of an inelastic collision, one object sticks to another. Okay? I.e., after the collision, object 1 sticks to object 2. Okay? In other words, or V final of 1 must be equal to V final of 2. Make sense? Okay? That's a very special case. That's a very important special case. Okay? It's a special case, but it's still very important. It's not the most generic one, but it's still very important. Oh. Final of 1 and final of 2. Okay? Same mass M undergoing object 1 object 1 has an initial velocity V01, V01, initial velocity V01 that's known, and object 2 is initially at rest or equal to 0, like that. Okay, so example 1. So, two objects of same mass undergoing elastic collision. That undergo, right? That undergo an inelastic collision. Find their final velocity. And see, there's no one else in my group. Okay, we'll figure it out, Destiny. We'll figure that out when we get there. Okay, so let's wait until 10 o'clock and let's message for Destiny. Let's see, admit. solution. So going back here. Okay, that's the situation. We want to find out their final velocity. And I'm going to go another step here. Like two objects of same mass having the same mass. Okay. You know, it's not necessary to make this assumption, okay? Because let's see. Consider the surface to be frictionless, right? Not necessary to make this assumption, but we're making it just to simplify the problem. And the situation is like the following. Go P initial equal to P final. Okay, like that. And we go ahead, Emma V naught. And by the way, let's do another additional step here. Instead of doing like that, you know, my P initial is going to be the P initial of object one plus the initial linear momentum of object number two, okay? Similarly, for the P final, we must have the same summation with a different subscript, okay? Like that. Because object number two is at rest, this term is going to be zero. And we already know that the initial velocity of object number one is V naught one. Okay, so P naught is going to be like that. We also know the final momentum of object number one is going to be something like that. Right? The masses are the same. And we can go another step. Okay, I'm gonna do the following. Here you go. I hate that. Like that. Good, better now. Yeah, same problem. Gotta watch for that. Because this is an inelastic collision, we must have, just like I mentioned here, right? We must have like that. Yes. Applying this relation to the above. I will plug that here. And I'll plug that here. I don't need the zero anymore, right? And now MVF should be the right side of the equation should be 2mvf. And don't forget, I want to find out what's vf. That's what I'm trying to find out here. The equality is this one right here. Mass cancel with mass. That's the next step. And finally, the final velocity should be V01 divided by 2. That's the simplest problem you're going to see out there. Okay. Simplest problem, simplest collision problem. 1D collision. M1 equal to M2. V02 equal to 0. 1D inelastic collision. One-dimensional inelastic condition, M1 equal to M2. Like that. M1 equal to M2. Right? V02 equal to 0. And then you can come up with another one. What about next level of difficulty? Next level of difficulty, it's example 2. Two objects of different masses. Different masses. M1, M2. One D inelastic collision. 1D inelastic collision. Two objects of different masses, comma. Two objects of different masses. In other words, M1 and M2, right? V0 at rest. Find their final velocity. Find their final velocity. Consider the surface to be frictionless. Same process. It's just a little bit more difficult, this problem. Okay. P02 is still 0, but here we have to put M1. Here we have to put M1. Here we have to put M2. Similarly, because the inelastic collision, the final one must be equal to the final 2. Okay, here we keep it M1. Here we keep M1 and M2. Okay, now what's not right is this one here, right? No longer right. So we put VF in evidence. Like that. Don't forget we want to solve for VF. I'm highlighting it. Right? And the final result is going to be, we don't need that anymore. It's going to be M1 V01 upstairs, M1 plus M2 downstairs. Okay. Okay, next. That's one example. Inelastic collision. Oh, there's another example here that I call explosion. Explosion. It's not a collision, right? It's a separation. Explosion or separation between objects. We have two objects stuck together, and somehow, you have, let's say, a spring attaching those two objects here, but somehow you release the spring, and the objects are propelled in opposite direction. That's another problem. There's another type of problem of collision. Okay, so now another example 3. Consider two objects of same mass stuck together. Initially stuck together and at rest. Okay, it can be a gun and a bullet, for instance. Okay, a gun and a bullet, they're at rest and they're stuck together, right? Somehow an internal force is activated and the two objects fly apart. That's what I call an explosion. Find their final velocities. And going back here again, here it can be the case of a very large bullet, and a gun. It can be the case of that. A gun that has a bullet that has the same mass as the gun. It can be like that. It's not going to be very safe to handle a gun like that, but you can think along those lines. And then we have powder there inside. You ignite the powder and the gun push on the bullet and the bullet push back on the gun, right? And they fly apart. That's my system. The initial momentum in this case is going to be 0 because they are both at rest. Okay, here you go. The initial momentum must be equal to the final momentum, right? Let's go. Just like before, the initial momentum must be equal to the final momentum. The difference is that the initial momentum is going to be 0 because both objects are at rest. Both objects are at rest. Okay, left side is going to be, they both have the same mass. Okay. They both have the same mass. Find, you know, don't find their final velocity. Let's say find the relation. Find the relation between their final velocity. You don't need to pinpoint exactly their velocity. In order to find out their velocity, you gotta do something else, okay? So we do not have this case here. What we have next is that, you know, one should be equal to minus the other. And in the next step, the mass cancel each other. And we have that the final velocity of one is minus the final velocity of two, and vice versa. Final velocity 2 is minus the final velocity of 1. One flying in one direction, the other flying in the other direction. Okay? If you want to know the exact value, okay, if you want to know the exact value of the final velocity, comma, you must know the internal energy of the powder gun, right? That propelled the two objects, or the potential energy, the internal energy or potential energy, let's write down, or potential energy, which is also referred to the chemical energy of the powder gun that propelled the two objects. Like that, you got. Two objects, okay? So, so let's look at an example 4 now. 8, 9, 30. Okay, we still have 30 more minutes to go. Refer to the previous problem. Okay. Assume that the potential energy of the gunpowder, it's not a powder gun, it's gunpowder, right? Gunpowder. Assume that the potential energy of the gunpowder is U, and 100% of this energy is converted into kinetic energy after ignited. Find the final velocity in terms of U, okay? In terms of U. Solution. So now we're gonna go back right in here to this problem, and you go like that. Explosion or separation with non-internal energy. That is conserved after the ignition, okay? Like that. That's conserved after the separation. So here you go. Situation goes like that. The two objects are initially at rest. You can also say that the internal energy, initial internal energy is U. Okay. After this gunpowder is ignited, okay, we have a total kinetic energy that's going to be equal to U. Kinetic energy is going to be equal to U because of conservation. Right? Find the final velocity. Now you have a problem that's slightly more complicated. It's a little bit more difficult because it requires not just one equation, but two equations. It requires this equation here. So you go, I'm going to put everything here at from the very beginning, right? Initial momentum is conserved. And we must also have that total energy must be conserved, right? Initial kinetic energy plus initial potential energy must be equal to the final kinetic energy plus the final potential energy. Because the two objects are at rest, initially at rest, the initial kinetic energy is 0. Okay, at the end, you used up 100% of your initial potential energy, so your final potential energy is going to be 0. Instead of using U, gunpowder before explosion, I'm going to use a different notation here, so you don't get U naught. Okay, in terms of U naught, it's better like that. And here too, instead U, writing that U, let's keep like U naught, non-value U naught. Non-value U naught. This one is 0. Don't forget this one is the final kinetic energy, and the final kinetic energy must be the final kinetic energy of 1 plus the final kinetic energy of 2, which is same masses, right? So those final velocity of 2 should be equal to the final velocity of 1, according to this result here, right? Let's put that step by step, right? Final velocity of 1 plus final velocity of 2, using the result of the previous problem. Final velocity of 1 is equal to final velocity of 2 with a minus sign, but because you're squaring, I'm going to emphasize that here, okay? I'm going to emphasize here that 1 is minus final velocity of 1. Like, here you go. Now I can raise to the power, okay? Because we're squaring that, right? The negative sign goes away. Okay, because we're squaring, the negative sign goes away. And we are left with MVF1 square, like that. Which can be further simplified to MVF square. Okay, and finally, we can get that's the equation. We can get our relation in terms of U naught. U naught divided by M is V squared. Vf is square root of U naught divided by M. Vf is square root like that. Okay, so now this problem is a little bit more complicated than the other one, than the inelastic collision, because now we have two equations instead of only one, right? This problem is a little bit more challenging than the inelastic collision one, because we have a system of two equations on conservation of linear momentum and conservation of energy. Okay. And then we can go ahead and look at another one. Example 5. Another type of collision, another type of 1D collision. The collision, okay? Totally elastic collision. By definition, a totally elastic collision is a collision where the energy of the system, where the mechanical energy of the system is conserved. Okay. Let me see if I have a drawing here. It's gonna be like that. Okay, let's see. Before we move forward, it's totally elastic collision, right? Let me just tell you what. So I'm gonna practical examples of an inelastic collision. Practical examples, not practical examples, of real life examples of inelastic collision. Going back here to inelastic collision, right? Then we go back to totally elastic collision. Collision between two objects that have Velcro attached to them. Okay, here you go. I'm gonna put it here. I'm gonna give you only two collisions between that have Velcro attached to them. You have one side of the Velcro in one object, the other side of the Velcro in another object. You go ahead and make them collide, they stick together and they move, right? And they move together. Another important example, collision between two cars. Nowadays, engineered cars are engineered to undergo an inelastic collision to preserve the lives of passengers. Okay. In this case, the frame of the car is wrecked, but the lives of the passengers are spared. In other words, the frame of the car absorbs most of the impact, absorb most of the force of the impact. Okay, here you go, real life examples of an explosion. Here you go, real life example of an explosion. A gun and a bullet being fired. Okay, and we have this other situation, which is a situation totally elastic collision. Example: balls in a pool table. You have played pool table, right? If you have played the pool table, you should have noticed that their collision is not inelastic. Instead, it is an elastic, and almost it is a totally elastic collision. Okay, in this case, both linear momentum and energy are conserved. That's another level. This type of problem, is a higher difficulty problem. So let's go. First of the now example 5, right? Example 3, example 4, example 5. Okay. Consider. I'm gonna copy part of it. You know. So objects having the same mass undergo a totally elastic collision. Totally elastic collision. In other words, after the collision, object 1 bounces off object 2. Velocity v0 that's none, and object 2 is initially at rest. Find their final velocity. Consider the surface to be frictionless. The surface along the surface where they move to be frictionless. Okay, and now we're gonna go back right in here. Here you go. I have this first object, mass m, initial velocity v0 second object, mass m, initial velocity 0 at rest. They come into contact. Object 1 propels, apply a force to object number 2. Object number 2 applies a force to object number 1 according to Newton's third law of motion. Oh, no, this one, that's not what it is. Must be this one here. This one here. For some reason, I put it, I'm going to erase this one right now. Yeah, it's this one right here. Nope, not this one. Totally, here is going to be totally elastic collision. Totally elastic collision. Okay, object number 2 is at rest. Object number 1 is moving towards it. Okay, object number 1 comes in contact with object number 2, applies a force to the right on object 2, and object 2 applies a force to the left on object 1. Okay, and then what's going to happen to the final velocity of 1 and the final velocity of 2? Okay, you go. Final velocity. I want you to find out their final velocities. Okay, find their final velocities. Like that. And then we gotta do exactly what we did before. What is that? Example number 4. Yeah, we gotta do exactly what we did here for this case here. Not only linear momentum is conserved, but total energy is also conserved. Okay. In this case, okay, I'm gonna hit right. Let's see here. Let's see if I can save it. Okay, yeah, I'll be able to save it. Let's see. Yeah, I'm gonna do that side by side. Next, right? Here. Here you go. You're gonna have P01 plus P02. I am doing vectorial notation here, but because it's one-dimensional collision, we can remove the vectorial notation from those letters. Okay, P final 1, P final 2. Okay, don't forget that U0 is equal to U because they're propagating the same surface, right? Okay, because the objects do not change height, right? U must be equal to U0. U final must be equal to U initial. If U final is equal to U initial, I apply this condition right here, right? And this term here is going to cancel out this term. And now I'm going to go for, this one is going to be 0. I'm going to put 0 here. This one is going to be V01. Two masses. The masses are the same. And then you're going to get V0, V final 1, and V final 2. What we're doing here, we see in the pool table, okay? This type of problem that we are doing here, you know, this U0 goes to the other side, right? And I get the simpler equation in which the initial kinetic energy is equal to the final kinetic energy. Another step, here you go. This is a system of two equations, okay? I'm doing everything according to the book. Here you go. And I'm going to remove the vectorial sign because it's one-dimensional problem, okay? I'm removing here the vectorial sign. Initial kinetic energy must be equal to the final kinetic energy. And I need to do one more step here. This one more step is going to be initial kinetic energy. I don't want this M like in that position. Okay, now we have it. Like that. Let's not forget. Oh, I'm gonna put one more step here at the top, okay? Kinetic energy, final kinetic energy of 1. Final kinetic energy of 1 plus final kinetic energy of 2. And I can break it down in final kinetic energy of 1 and 2. Oops. And final kinetic energy of 2. Okay, like that. Oh, by the way, we can cancel out this M, right? I should have done that before. In my next step, I'm going to simplify those guys here. Half M, 953, we're almost there. And now look what we have. I'm going to highlight those values that we do not know. We do not know V final of 1. We do not know V final of 2, right? Looking at the above, system of equations, we have 2 equations for 2 unknowns. Most of the time, we have the same number of equations and unknowns. Most of the time, not all, okay? We can solve the problem. So if you have one equation for one unknown, we can solve the system of single equation. If we have 2 equations for 2 unknowns, we probably can solve that, provided the 2 equations are independent of each other. If we have 3 equations of 3 unknowns, maybe we can also solve it, provided the 3 equations are independent of each other as well. Okay? So what we can do, we can start trying to solve this equation. How do we do that? One way to do that is to write one unknown in terms of the other unknown. I'm going to write down VF2 in terms of VF1, and then substitute this value here right in here, right? That's how you do it. The substitution of variables, the method of substitution of variables. Let's V01. When we do something like that, then we reduce our problem to a problem having one equation at a single unknown. See that? What happened? It's like magic, right? Now we have just a single unknown, V final 1 and V final 1. So in principle, we can solve this equation. We can solve this equation by expanding the right-hand side. Okay. Minus 2V01, V final 1. And then we have V final 1 squared, like that. Okay. We still have our unknown here. And let's see if we can solve it, right? I will just repeat the first equation. I don't need to do anything else here in this first equation. I'm going to just, make it look nicer. I will use this first equation later on. Okay. Once we solve VF1 in terms of the known parameters, we'll be able to solve this one here. And here you go. That's what we have. right? This V naught, okay, is gonna cancel out with this other V naught. I'm gonna put them in red so you can visualize it more readily, right? This VF final one is gonna combine with this V final one. Okay, it's gonna be a 0. This is gonna be a 0, right? I will combine the final one with this other the final one, and we're going to end up with a parabolic equation. We're going to end up with a parabolic equation. I can erase this one. When we erase this one, the 2 goes away. Okay, and now I can put the final one in evidence. When we put the final one in evidence, this V squared reduces to V. And I'm gonna put the, the 0 on the right side. We're almost done with this problem. That's all it takes to. Now, this equation here has 2 possible solutions. Okay? This equation has 2 possible solutions. Okay. The second equation has 2 possible solutions. I don't need to repeat it here, right? Because it's already there. One of the solutions is, the final one equal to 0. The other solution is the final one minus V naught 1 is equal to 0, which, by the way, reduces to the final one equal to V initial 1. And now we have to analyze to find out which solution is the most appropriate one. Okay? I'm going to erase this guy here. Did I screw up here? Uh-oh. Oh man, yeah, it looks like I did screw up. Oh gosh. Well, I missed the. Ay. That's so sad. Let's see, I didn't notice that. Nobody noticed that before, right? Yeah, let me reorganize that so you can refer to that more easily. Okay, this guy here is okay, it's gonna be like that. Yeah. I almost done this only now. I noticed that. Here you go, it's like that. Okay. Yeah. Okay, and now it's just a matter of reorganizing it. Another type of. Here you go. It's gonna be like that. Okay. Here you go. Okay. So how is that? What's happening here? Okay. With example 1 is inelastic collision, equal masses, one mass at rest, the other moving, right? Example number 2, different masses, inelastic collision, one inelastic collision, different masses. Example number 3, same masses, explosion, right? Example number 4, same mass, explosion, but I want you to find out the exact final velocity in terms of the internal energy of the system. And number 5 is totally elastic collision, same masses. And I'm writing here. Okay, so I finally got that. And now we have to analyze those 2 solutions. Which one is the physical one? Which one is the physical solution? Which one is the correct one? the final velocity of one is going to be 0 or is going to be equal to its initial velocity, right? That's what we have to analyze. Let's take a look. We have to visualize that right here. Okay, right here. Okay, one solution states that the initial velocity of one is v01, and the final velocity of one is going to be 0. What's going to that be? You know. So it means that this one is going to be at rest after the collision, and this one is going to move forward. Okay? It looks like it's reasonable, right? It looks like it's reasonable. The other solution states that the final velocity of one will continue to be v01. It's not going to change at all. Going back here, what does it mean? Final velocity of one will continue to be this velocity that you see right in here. It is as though as the first mass is just moving through the second mass. Okay? That's not a physical situation, right? Masses cannot go across each one, right? Is just like that, your pool table, right? Your balls in the pool table. V01, they undergo a collision, and the final velocity of 2 becomes v01. That's the first solution. The second solution, you know, what's the second solution means? First mass undergoes a collision with the second mass, and soon after the collision, it starts to go through the second mass as though it is a ghost, right? That's what the mathematical solution provides us. Something like that cannot exist in the real world unless the first mass is slightly shifted from the second mass. Unless you have a situation like that seen from the top, okay? Seen from the top. You know, in this case, there is no collision whatsoever. And the first mass continue propagate at v01. And that's what the mathematical solution is all about. Okay? So the correct, the more appropriate physical solution is the first one. In this case, after the collision, the first mass comes to rest. And the second mass, right? So here you go. Here's my system of equations again, right? And the second mass, we go using the first, I'm going to put like that, using the first solution. We have Norberto, we go. V final one equal to 0, right? Using the first solution. What do we end up having? V final one is 0. V final 2 is going to be V01. And the second mass moves with the same initial velocity of the first mass. Okay, so 10:06 right now. I want to go for a break very soon. Let's just tell you what we are doing here. Let's see. What are the chapters that we're covering, right? Remember, we are skipping 7.1. The first section, not the chapter, the first section of the chapter. Oops. Didn't copy. Let's go get that again. Right in here. Well, it's not. Oh, man, what's going on here? Ay. Didn't copy it. Let's try to copy it again. Third time I'm trying to copy the same thing. Here you go. Linear momentum, chapter 7, right? Copy, right? Copy. Now you should paste it. Okay, finally. Principle of conservation of linear momentum, we covered. We're doing collisions in one dimension. And very soon we're going to do collisions in two dimensions. Next time we're going to do collisions in two dimensions, okay? Let me unbold face here, just to remind me that we're going to do that next time. And 10:07 right now. Any questions? Oh, I gotta take attendance, right? November 8th. Let's see. We have 2 more minutes to go before we go in. Sky, are you there? I don't see Sky here. Tessa, this is not here. Destiny, are you here, Destiny?
Yes.
Okay, thank you. Gael is not here, right? Ridwan is here. Yeah, thank you. Ashley Isumo. I don't see Ashley here. No, at least Norberto Lopez. Hello, Norberto.
Yeah, I'm here.
Okay, thank you. Anabel Madrigal. I don't see Anabel. Vanessa Mena.
Here.
Thank you, Vanessa. Catherine Pacheco. I don't see Catherine. Camden is here, right? Is that Camden? 10:09. I'll give Canada attendance. Victoria Preciado. I don't see Victoria here. Alexis Richardson. I don't see Alexis. Marco Sanchez. Okay, thank you. And 10:09. Okay, we have 6 students. Okay, good. With me 7, and what I want to do, a break from 10:10 a.m. to 10:25 a.m. Okay. After the break, we start lab 5. So I see you shortly in 15 minutes. I'm back here. 10:25 right now. Let's take a look here. I'm going to upload the labs. 1. Oh, don't forget reports for labs 3 and 4 are due now, right? And I will upload the report, the spreadsheet, upload the spreadsheet for lab 5 now. Raw data. We're doing lab 5. Good, right? All folder, Physics 6. Okay, group 1. Okay, before, wait a minute, what am I doing here? Yeah, Let me do something first before. Oh. Okay, ignore that. Ignore this file here, group one. I have to make a slight change to it. Small change to it before we make a small change. Let's make sure everything is. Oh, that's 4. Oh, well. I don't want 4, I want 5. Let's make sure everything is right here. Yeah, that looks like it's right. Nothing wrong. That's lab 5, group 4. Let's see. Yeah, that's group. Okay. No problema here either. 5. Yeah, okay. And I gotta get back to my spreadsheet here. Let's see who is here first. Let's see. Sort group number. So let's see. Destiny, you're the only one in group 1, right?
Yes.
Okay. Let's see the other students here. Group 2. Read 1, you're by yourself today, huh? Read 1 is by himself. Group 3 is here. And we have only one student in group 4. Okay. So let's combine group 1, 2, and 4 today, only for today, right? Combine students of group 1, 2, 2, and 4, only for today. And then you figure out which, and you resolve among yourselves which, which spreadsheet you want to use, right? Let's do that. Exchange your contact information, and then you decide which folder you are going to use. Can be either the folder of group 1, the folder of group 2, or the folder of group 4, okay? Let's see here. It seems that way. Plumber buddies, yeah. Well, do you think the other students are gonna come, are gonna knock at the door here today, or they're just skipping? Ridwan, do you know if your group members are going to attend today, or they're just skipping today, Ridwan? I don't know the response from Ashley, but I can try. Yeah, try to message Annabelle. And what about you, Destiny? Do you know if they're going to arrive later today, or let's see. Tessa, it looks like Tessa dropped, right, Destiny?
Yeah, they both dropped. So
Oh,
it's
both dropped. Okay. Yeah. Okay. So let me take it out here. So they're not coming back. They're not coming today. And Gael. Okay, so maybe, since they both dropped, you might want to, let's see, let me talk to the other student. Marco, did you hear from Victoria and Alexis? No, you didn't hear from them? Did they say anything about that they're gonna drop, or they didn't say anything about that? You don't know? Okay, so let's do the following. Since Destiny is the only student left, oh, usually Alexis is here, right? Okay. Okay, so since Destiny is the only student in group 1, why don't you use folks group number 2 folder today, okay? Either group number 2 or group number 4 today. Let's do it this way. Decide among yourselves which one you're gonna use, either 2 or 4. I will. And okay, can someone share, please? Yeah, you have to share the link, right? You might want to address this message to the other students, okay? Let's see here. No one, everyone, yeah. Okay. Share group two, yeah. Okay, so send the link of group 2 to Destiny, and then you should also send the link of group 2 to, who's that? Marco Sanchez, okay? Marco Sanchez, don't forget to give the email address to Ridwan to exchange. It's gonna be Destiny and Marcus. Yeah, that's right. Destiny and Marcus. Don't share the link here in the chat. Just send it by email. Okay, since this link for this group link is considered somewhat private. You can also use Canvas, right? Canvas also has email capabilities. And let me fix that. We're going to be using group number 2. Oops. Group number 2, group number 3. And group number 4. Only 3 groups today. Group number 2. Yes, that's right. Destiny and Marco Sanchez. Yes, I'm confirming that. Group number 2. So you have your spreadsheet. Group number 3, you have your spreadsheet. Oh, okay, okay. Okay, thank you. Sorry, read one. Okay, so group number 2, 3, and 4 have the spreadsheet. Now, wait a minute, 4 as well? 4 doesn't need it, right? Yeah, 4 doesn't need it. Only 2 and 3. Let me. Okay. So only 2 groups today. Let's take a look. This one here. I will walk you through the experiment one by one. Okay, so what we have here is Newton's second law of motion experiment. There are several ways of verifying Newton's second law of motion, okay? Several ways. This is just one of them. I think it's the nicest of all. Break. Okay. Lab 5, Newton's second law of motion. I will put those two here at the top. One. Yeah. Okay. Report for lab 2 and 3, 3 and 4 are due now. I uploaded the spreadsheets for groups 2 and 3. 3, 2 and 3, right? I didn't do for the other groups because there are no other students there. Those groups are not working here today. Okay, so there are several ways of verifying Newton's second law in the lab, second law of motion in the lab. The one we will do today is using the so-called Atwood Atwood machine, right? Let's make sure that's the right the configuration. Atwood machine. Yeah, that's the right name. Atwood machine. Let me show you how does it look like. Let's see here. Is Atwood machine interesting? Okay, here you go. The Atwood machine. This is an application of the Atwood machine. Okay, this is not the Atwood machine per se, but what you have here is a pendulum, right? That's powered by this Atwood machine. And the simplest, let's see, here you go. That's the simplest configuration of the Atwood machine. The Atwood machine is made of a pulley, a suspended pulley, and two masses attached by a string. Okay? If you look there at the Wikipedia, you're going to see something like that. Here you go, let's take a look here. The Atwood machine was invented in 1784. It's a very simple device, right? By the English mathematician George Atwood as a laboratory experiment to verify the mechanical laws of motion, Newton's second law. That's what he's mentioning. With a constant acceleration, Atwood's machine is a common classroom demonstration used to illustrate principles of classical mechanics. The ideal Atwood machine consists of two objects of mass 1 and 2 connected by an inextensible massless string over an ideal massless pulley. Okay, inextensible means it doesn't stretch, but it's a negligible mass. Both mass experience uniform acceleration. Something wrong here. Okay, when m1 equal to m2, that's not true. Okay, it's not uniform acceleration. Uniform velocity. They made a mistake here in Wikipedia. First time I see a mistake here in Wikipedia. My machine is in neutral equilibrium regardless of the position of the weights. Okay, so it's not uniform acceleration. Okay, uniform velocity when m1 equal to m2. Okay, so let's I'm going to walk you through the derivation of the whole thing and how to put the experiment together. Okay, and Okay, this one here. Choose. Lab slides. No, was that lab slides here? P37. I need to start organizing, some of my slides of the courses. I have the lab slides organized, but not the notes. Okay. Let's see if this one's a good one. Yeah, it's not the complete. What a shame. I thought I had the whole thing. Let me close this one here. Wow, it's gonna take a long time. Okay, now, yeah, that's what we have. When we perform this experiment in the classroom, the drawing is not complete here. I will try to get it completed so you understand how we put together this experiment. Okay, we start with a table for this experiment. Okay, so here go. I'm gonna do that. Let's see here. Zero. Okay, I'm gonna put my table at the very middle. I need to do this table a little bit larger. A little bit taller, a little bit larger. Legs a little bit thicker. Oh. And I want to make this line thicker. Yeah. So that's where we start with. We don't need that anymore, but table for support. Okay, equipment, right? We start here with the list of equipment. Equipment. One. Table. Good. Table for support of the equipment. Give me a few minutes here. I'm hunting down here my notes from the previous semester. It doesn't look like it's here. Is here, lecture notes, lab notes must be here. Lab 5, let's see. That matches. Okay. Okay. So it's like that. You go. Table for support. And then what are you gonna do next? What you need next? You're gonna need a clamp. I'm gonna make a drawing of a rod clamp. Table support. And this rod clamp has a screw here that attaches it, that clamps it. Can you picture that? Okay, so table for support, rod clamp. Okay. This clamp clamps to the table, but it can also clamps to a rod, to a very tall rod that goes here. Clamp here and clamp in the back that's not shown, that you cannot see it. So here you go. Table, rod clamp. Next. Oops, this one. Next is going to be a rod. And I'm gonna copy this guy here, use it as my rod. Kind of a small, okay, like that. Bring to front. Bring to front. What? Huh, interesting. Okay, no, it's the problem. Yeah, okay. Here you go. Okay. And that's the rod. Next. Okay, so I start with the table. Table for supporting the experiment. We put a clamp on the table. Let me get this clamp. We have this clamp there at the college. Have this clamp at the college, okay? And then we get a rod. This rod is going to support our pulley. I'm going to make this guy a little bit more to the right, to the left. Let's see. Yeah, good. I got it in the right place. What you have here is just like something to clump the rod, and this rod is used to support a pulley, frictionless pulley. I'll get it here. Okay, here's my frictionless pulley. Frictionless pulley. The frictionless pulley has a clamp as well. There's a clamp, which is not shown, which is not illustrated here. Rod clamp, rod, frictionless pulley with another clamp. Okay, this pulley is clamped. This pulley is clamped to the rod table. Rod clamp. Clamped to the table. Clamped to the table. This one, rod. Clamped to the rod clamp. Right? Frictionless pulley with another clamp. This pulley is clamped to the top of the rod. To the top of the rod. What's next? I don't need that anymore. I don't need that anymore. Okay, so next, you suspend two mass hangers. Okay. See, that's the Atwood machine, right? Two mass hangers. Better now. So, two mass hangers attached by string. Pass the string through the pulley. Okay. See where we are here. Copy. We didn't get to this table yet. Camden, good. Two mass hanger, okay? Two mass hangers attached by string. Load the mass hangers with load one side side of the mass hanger with mass slots. Load both mass hangers with mass slots. One side will have a total mass M1 and the other side M2, like that. We use those mass hangers before. Not only we use the mass hangers, but we also use the slotted mass before in the experiment of the force table. Okay. Recall that we use the mass hangers in the force table experiment, right? Recall that we used the slotted masses, the slotted masses in the force table experiment. Okay. And now we can start talking about our tables here. Do you see here M1 and M2? We're going to need the G. The G is already given, 9.8 meters per second square. And here you go, M1 and M2. I load the left side in this first measurement. I loaded the left side with a mass of 552.6 grams, and the other side 581 grams. M2 is greater than M1. So because M2 is greater than M1, the system will accelerate in the direction of M2. Like that, you go. M2 greater than M1. Okay, and I put on purpose, I put the M2 higher than M1 because the system is going to accelerate in this direction, right? Let's write that down here. You go, M2 greater than M1. Stretch, okay? Next. Okay, so we start with a net mass equal to that, right? 552 in the M1 mass, 581 in the M2 mass. And on the top of that, we are also going to suspend the mass to a height h. And that you gotta measure. Not this one here. Let's see. Oh yeah, right in here. I need this one. Good. Oh, by the way, I need to put the scale there, right? Here you go. Mass hangers attacked by string, load both, okay. Measure M1 and M2 with the provided scale. The scale has a resolution of 0.01 grams, which is equal to 0.1231 kilogram. Don't forget you need that. to display the masses with the proper number of significant figures. I want this one out. Here you go. Yeah, proper number of significant figures, right? What else? What's next? M1 and M2. Here you go. M1 and M2. Like that. Next, measure the initial height of M2. Of M2 using a meter stick. Initial height H, right? H of M2 using a meter stick. Next, let's see this one. I'm gonna do that right now. Here you go. That's the one I want. Here you go. Don't forget, meter stick. Meter stick has a resolution of 1 millimeter, which is equal to 0.001 meters. Okay, I don't need that anymore, right? I don't need that anymore. Okay. Now, one more. Note, see that this is my system. My system is, right? The dashed line indicates my system. My system is mass 1, the massless string, and mass 2. That's my system. And we are going to, once you load, you gotta do something that's very important, you know. It doesn't look that important, but it is very important. Load both mass handles with masses lots. One side we have total mass M1, and the other side you will have total mass M2. Here you go. We gotta do something else before here. Oh no, so you still have to measure the masses M1, right? And then make sure you wrap the slotted masses in the mass hanger with masking tape. Make with masking tape to ensure they will not fly, to ensure the masses, right? The masses will not fly away when they impact the floor. Very important. You know, that's a safety issue. Keep in mind, this is a safety issue. This is a safety issue. You don't want to hurt anybody. Imagine those heavy mass flying all over the place, you know, hitting your foot. This is a safety issue, okay? So here you go, masking tape, not making tape, right? Masking tape. Here you go, masking tape, scale, meter stick, everything in italics. Mass slots, they are all mass hangers. They're all part of the equipment. Frictionless pulley. Metal rod. Let's put a metal rod here instead of rod. Rod clamp. And of course, you need a table to perform the experiment here as well. measure the initial height, and the initial height is documented right in here in this column, H, everything in meter, right? We usually start with 1.5 meters. Ideally, you will, the higher the masses, start, the better, by the way. What's next? Okay, I will get back to that, okay? Next, okay, here you go. Here's the weight, right? The forces applied to my system. Okay, I'm gonna put it this way, like that. Here are the forces applied to my system, W1 and W2. Weight 1 and weight 2, right? What you gotta do now, because weight 1 is greater than weight 2, the system is gonna rotate in the counterclockwise direction, okay? Okay, what you have to do now, release mass 2 and measure how long it takes to reach the floor with a timer. Can be your cell phone timer. They usually have a resolution with a resolution of 0.01 seconds, okay? Your timer. I'm not gonna put cell phone timer, I'm gonna put a timer. Can be the timer in your cell phone, but it can be a different timer as well. So that's what we do right in here. And do that, repeat repeat that 3 times. Repeat 2 more times. Repeat 2 more times. We have T1, T2, and T3. See spreadsheet. T1, okay. T2, and T3. See spreadsheet. Okay. So what we have here, raw data, raw data, raw data, raw data, raw data, and raw data. All of that is raw data. Okay, all of that is raw data. Then what's next? Okay, transfer sum of the mass from M2 to M1 while maintaining the relation M2 greater than M1. Okay. Transfer some of the mass from M2 to M1 while maintaining the relation and ensuring that M2 plus M1, M2 plus M1 remains constant throughout the experiment. Okay, that's the key of this experiment. Ensure that M1 plus M2 remains constant, but still ensuring that M2 remains greater than M1 throughout the whole experiment. So you still have an acceleration. Okay. That's when you get the other values. Okay. So here you go. See 555, 552 for M1, 581 for M2. Next, M1, M2 is going to be less than the previous value. For 581, it's going to be decreased to 580, but it's still greater than M1, which is at 553 now, and so on, okay? Along the process, M1 plus M2 will remain constant. This is a result. Everything else is raw data. What's next? Next, you're going to take the average of those 3 times. Okay, make sure you have the right number sequence figures, 11, 15. And then we calculate the acceleration of the system using the kinematics equation. Okay, so here go, going back here. Transfer some of the masses while repeat the relation. Okay, repeat this procedure for a total of 6 measurements. Measurements. Okay, we have 6 measurements right in here. 1, 2, 3, 4, 5, 6. Okay. Calculate the average. Right? Calculate the acceleration of the system using the kinematics equation. What the kinematics equation is? The system is accelerated, so we must have y equal to y naught plus v naught t, right? Minus half a t squared. That's the kinematic equation that you gotta use. Initial velocity is 0. Consequently, the second term disappeared. This term disappeared. The final height is going to be 0 because it's gonna be the floor, right? Final height is gonna be 0 because it's gonna be at the floor of the classroom. And now we solve for the acceleration. This is measured. This is measured. This is measured. This is a result from the average of the 3 measurements, right? And we get the acceleration. Like that. Don't forget h, y naught is in reality h, right? In reality is h. And then we calculate the acceleration as being 2h over t squared. And I put my a right here. Let's take a look at my spreadsheet. 2h
Professor, I
over
have a
t
question.
squared. Yeah.
How come the formula is -1/2 instead of +1/2 to
Well,
get the
for the
difference?
same reason we have been doing from the very beginning, right? Let me show you. Let's see. Remember, right, how we are doing for projectile motion, right? So
because it's down.
it has to do with the axis, right? The axis is like that, this upwards axis, right? The acceleration is downward, so it must be minus acceleration, Okay,
Oh, okay.
that's the reason. Let's see. Let me put that here. That's y-axis. I'm gonna make it a little bit thicker. And right here is gonna be the origin of my y-axis. Right? Makes sense, Camden? The acceleration is downward,
Yes.
the axis is upward, so the acceleration must be negative. Okay.
Yes, now I understand. Thank you.
Okay. So I don't need that. Okay, I don't need that. Oh, and let's see, did I put masking tape there? Masking tape, yeah. I'm gonna put that in boldface so it's easier. So it's easier for you to locate, right? All the equipment and procedure, right? And procedure. Table, rod clamp, metal rod, frictionless pulley. There's another clamp, mass hangers, mass slot, scale. Here we go. Scale, masking tape. What else? Meter stick. Okay, meter stick. Timer. Right? Transfer some of the mass M2 to M1 while maintaining the relation and ensuring, right? Repeat was total 6. Calculate the average. Calculate the acceleration of the system using the kinematic equation. Okay. Oh, and also calculate M2 minus M1. There's a reason. Okay, calculate M2 minus M1. There's a reason for that. Calculate M2 minus M1. And why do we do that? There's a reason. Calculate M2 minus M1 to find the net force of the system, the net force acting on the system, right? The net force is, let's see here. Yeah. Right? W2 minus W1. What's going on here? Okay. Now we're back, right? So, and that's what I did here. M2 minus M1. Don't forget to display the proper number of significant figures. And here is the net force, right? Net force. Accordingly, the equation, so we have the following. We have this net force. Net force equal to M2 minus M1 times G, right? Is equal to the net mass of my system. See that? The net mass of my system, M2 plus M1 times the acceleration. Here you go. We already calculated the acceleration in one way using the kinematic equation. And now we can also calculate the acceleration in another way using Newton's second law of motion. Okay? And then this summation is kept constant throughout the experiment. This acceleration is going to change throughout the experiment. I'm gonna highlight what changes and what doesn't change, okay? So we have this equation right in here. This change. This also changes. But this one here remains constant. So what do we do? Okay, what do we do? We are going to plot plot F net along the y-axis and A along the x-axis. That's what you have to do for this experiment. Oh. Oh, Jesus. Good. Plot F net along the y-axis and A along the x-axis. According to this equation, you're supposed to get a straight line with slope m1 plus m2. According to the above equation, you are supposed to get a straight line with m1 plus m2 as the slope. Okay, that's what you have to do. First step, right? First step, plot the graph. And I'm going to plot my own graph. Net force, acceleration. Don't forget, this acceleration was obtained using kinematics principles, not Newton's second law. Newton's second law is independent of the kinematic equation. So if you did everything right, if the data is good, right, it's a good data, a little bit off here, right? But it looks like in general is a straight line. Let's that's what I'm getting here. So you gotta do the same for your own graphs. I will I gotta make sure that this data here, format, axis. Let's see, is that the one? Labels, numbers, right here. I'm going to put it numeric format. Let's see how many decimal places I need. 4. I don't need 4. I need less than 4. I need just 1, 2. I need only 2 decimal places here. Okay, so that's my graph, but there's more to it. I can optimize this space, right?
Professor,
Yeah.
can you plot the graph one more time?
Yeah,
please?
you go. See that? Net force, you highlight this one here. And then you highlight the acceleration. Okay? Insert.
But mine is not linear.
Yeah. There's a little trick here, right? First you highlight this one. Then what do? You press the control key and highlight the second one. You gotta press the control key while you highlight the second one. The second column. Did it work?
Let me try it one more time. It's
Supposed
still
to
not
work.
linear graph. It's just kind of weird. I mean, it's kind of linear except for one dot, like one plot, I think. I don't know what to do with that.
Okay, your group number?
Group number 3.
3. 5.
But when you apply trend line, it looks like linear, but it's like by looking at it, it's not exactly
Okay,
like that.
yeah. I'm going to highlight force and acceleration. Insert, chart. Yeah, that's right. You have some data that are not very good. It looks like this one here is your outlier. Okay.
Okay.
But you should get I know maybe this one is the outlier. Let's take a look. Maybe this one is the outlier. Let's see. I'm not going to add trend line, display equation chart. Okay, that's what I'm getting here. 1.1572 for the slope. 1.1572. See the R square? Because of those outliers, you're getting an R square relatively small, 0.7375. You know, if was doing that in an actual experiment, I would ask my students to repeat this data point here.
Okay.
I'll ask my students to repeat this data point. But let's see if you still get a good value for the slope or not. Okay, let's see if you still get. You gotta put expected value for the slope right in here. Oops, 1.15. 1.1572. 1.1572. See, I get only 1.74%. Even though the R square is small, even though you have that outlier that interferes with the curve, right? With the straight line, you still get a very good percentage difference, only 1.74%. So don't feel intimidated if you see something that doesn't look right. Even though this point is a little bit off, right? Everything else seems to line up properly. So like I said, this guy is an outlier, and if we're performing an experiment in the classroom, I would ask you to repeat this measurement here. Okay.
Thank you.
Okay. So 11:30. So we did everything that you need to know. Let's see, this one here, first run. I don't need this. I don't need any of that. I can erase it. Here you go. Good. Now you're in good shape. Let's review this experiment again. Here you go. Table, rod clamp, rod attached to the rod clamp. Then I don't need that. Pulley. Pulley is a clamp. I gotta fix that. Pulley is a clamp. Frictionless pulley with a clamp. Let's see. Add hanging masses. Add slotted masses to the hanging to the mass hangers, not a mass hanger. The mass hangers, 2 mass hangers. You go add mass hangers. Add mass hangers. Okay. Let's do it again. Table, rod clamp, rod, frictionless pulley is a clamp, add mass hangers. I don't need that here. This one comes afterwards. I don't need this one yet here. It's gonna come afterwards. Okay, add slotted mass to the mass hangers. M2 greater than M1, M2 and M1. Next, system, free body diagram, no? System, no, free body diagram. Free body diagram. This is the Atwood machine, right? Free body diagram. Free body diagram. And from this free body diagram, we get the net force of our system equal to MA, right? And so what we did in this experiment, what we did in this experiment, we determine the acceleration in two different and independent ways. One using the kinematics equation, and the other using Newton's second law of motion. Okay. And now we can move on and we can move forward. And what do we have to do? Plot the graph, right? After plotting, fill up the units, display the proper number of sig figs, right? Find out CL. After plotting, fill up the units. Well, you gotta do something else too, right? Fill up the slope in table. What's the table number? Fill up the slope in table 4-5. 4-5, and check the percentage difference. After plotting, display the proper units. Display the proper number of significant figures. Find CL. That's what you have to do. 11:36 right now. Can you do that in the next 20 minutes? I'll give you a little bit of time before I call you. Okay, today is next thing I'm gonna ask you is to plot, if you plotted the graphs. Hello, Destiny, did you plot the graph?
Yes.
Okay, you did, okay. After plotting the graph, did you compare percentage difference? Did you get the percentage difference there?
I'm still kind of working on that.
Okay, still working. Good. So read one. Did you plot the graph? Let's see. I haven't got the percentage difference yet. Working on the units. Okay. You plot the graph. Yeah, okay. So you gotta put it here, units, right? Units comes first. Well, actually, the percentage difference comes first. Working on the units. You're also working on the units, Destiny? Hi, Destiny. Are you still working? Are you also working on the units?
Yes.
Okay, good. So next, Norberto. Did you plot the graph, Norberto?
Yeah, I was able to plot the graph.
Okay. Did you finish the units?
No, I haven't. I'm still working on that and the difference.
Okay. You're also working on percentage difference. Okay.
Yeah.
Vanessa, you plot the graph? Is Vanessa here? Yeah, Vanessa is here. Hello, Vanessa, are you there? I'm gonna put a little star here on Vanessa. Okay, next is Camden. Did you plot the graph, Camden?
Yes, I did.
Did you finish the units?
I'm working on it.
Okay, and what about the percentage difference?
I'm still working on it, but I have a question, Professor. So, we need to change the all the units format to numeric or number into number or just
Yeah. Mhm. You
Oh,
change
okay.
everything is in scientific formats, and then you have to change to units to the number format using that rule of thumb that I told you, right?
So
Remember the rule of
six
thumb?
decimals, right?
Huh?
6 decimals.
Six decimals?
Yeah.
No, it's not
Or
six decimals.
Oh,
Check
it's not.
again the notes. Check the notes again. It's not six
Oh,
decimals. Okay.
okay. Thank you.
Okay. Next, Marco Sanchez. Did you plot the graph, Marco? Yes, working on the units, and I presume you're working on the percentage difference as well, right? Okay. Okay, good. So I'll give you a little bit more of time. We have 20 more minutes to go. I will walk momentarily away from my computer, okay? In this meantime, I would like you to continue working on this spreadsheet. Okay, so I'll be back shortly. Oh. Okay, I'm back here. So 7 more minutes to go. Do you have any questions?
Professor, what's the net force unit?
Well, what's the unit of force?
Um, N.
Well, you answered the question, right?
Oh, that's it? Okay.
Yeah, net force is units of forces, right?
Okay, thank you. Yeah, I was thinking about like kilogram meter per second square or something like that.
Yeah,
but-
and kilogram meter per second square also receives which name?
Oh, yeah, because F equals MA, right?
Yeah, so
Oh, okay. Oh, okay. Okay, that makes sense.
kilogram meter per second square is equal to Newton. Okay. It all comes from the second Newton's law. F equal to ma. I have one. I'm having a hard time understanding how to set the unit. Okay. Okay, the unit of the slope is what? The unit of the rise divided by the unit of the run. Right? Unit of the slope. Unit of the slope. Unit of the rise. Unit of the rise is the Newton. Right? Divided by the unit of the run. The unit of the run is meter per second square, right? Like that. But then you know that Newton is kilograms meter per second square, right? And then what happens? What happens? Meter square cancel out with meter square, right? And you get what? Oh, I'm not sharing the screen? Okay. Thank you, thank you. Okay, here you go. Unit of the slope, right? Unit of the slope is the unit of the rise, which is Newton, divided by the unit of the run, right? But the unit of the rise, which is Newtons, is also kilogram meter per second square. Here is force, here is acceleration. Okay? Meter second square cancel out with meter per second square, and what do you get? You get kilogram. Which should be, the slope is what? The slope is, just like I mentioned before, right? Here you go, the slope is this term here. M1 plus M2, which has a unit of kilogram. Okay. 3 more minutes to go. Can you finish on your own now? Okay. So, all right, we can stop here and have a good one too. And by the way, this lab report is due next week. Let me write that down here. The report for this lab. Okay. Report for, oops.
Okay.
Are you talking to me, Camden?
Oh no, I was just talking to myself.
Okay.
So the lab is due next week, right?
Is due next week. Yeah, next week is 15th, November 15th.
Professor, I have a question. So I think I accidentally pressed something and messed up my what's that called? Time 3.
Okay.
Do you know how to like reverse it back to the default value? Mine is like all pound, like all pound
Well,
sign.
all you gotta do is to press Control Z, right? Did you do that?
But I think I've done this like way before. So I input like multiple values after this incident.
Okay, you what you can do, you can download the spreadsheet that is there in your group folder. That spreadsheet was not changed. Okay.
Yeah, and then just copy it and paste
Yeah,
it.
that's right.
Okay.
If you did
Right.
if you modified the values, numerical values somehow, you can recover it by downloading the spreadsheet that is already in your group folder.
Oh, okay.
Or you can also interface with your group members as well.
Oh, okay.
Okay.
Oh, by the way, Professor, how to get the net force value is I know I read the manuals and everything. Is that then m sub 2 g minus m sub 1 g, right?
Yeah, right in here. It's already calculated for you.
So that I just need to so do I need to get the average value as
No.
a no?
No, you don't get the average value because this is a variable. This is a variable parameter.
Then what do I need to type in the values?
Where? Type where?
Table 4.4, the graph. I mean, when you scroll
4.4.
down.
Okay,
Yeah,
that's
there.
the equation. Remember, that's the equation. That's the regression equation.
So what do I need to type into
Oh,
that?
the regression equation.
The whole equation?
Yeah, that's right. The regression equation. You are plotting f net at the vertical and a at the horizontal. Okay. Just like
Oh, the one that the graph one, right?
yeah, here you go. Regression equation here. This equation here.
And then what do I need to type?
Well, here you go. The regression equation. The regression
Oh, okay.
equation.
Oh, okay.
Okay. Here is f net, and here, oops. Here is f net, and here is the acceleration.
Oh, okay. So the x becomes the acceleration.
Yeah, that's what it's all about, right?
Okay.
We plot a along the x-axis.
So the number values is 6, right?
Number value, what number value?
N. The n.
What number values are you talking about?
Oh, table 4-4.
Table 4-4?
Yeah.
Yeah, what about it? Here,
Yeah, the total values are 6, right?
6. Okay, you gotta count, right? How many you have here, right?
Yeah, 6.
The number of data points, the number of pair of data points. And then you gotta put R squared, you gotta put the regression equation, and then you gotta write down the CLs as well.
Oh, how about the slope?
Okay, what's the slope that you got for your graph?
I got acceleration versus force.
What is the slope that you got for your graph?
Well, I don't know, to be honest.
Well, did you get the regression equation?
Yes.
Okay, what's the slope of the regression equation?
Acceleration.
Oh, here you go. Okay, here you go. That's your graph, right? Group 3. Is that group 3?
Oh wait, it looks quite different than yeah.
Hey, it looks like a different one. Your group 3, right?
Yeah, mine has the outlier.
Yeah, why is that? No, something happened here.
Oh.
Yeah, okay, that's the one. Okay.
Yeah.
Okay, where's the regression equation here in this graph?
The straight line.
Yeah, but and what's the slope here of this regression equation?
Is it at the end?
No, let's see here. Here you go. Okay, here you go. Okay, I'm gonna right click, add trend line, right? Okay, R square. We have R square here, right? And now I'm going to display the equation, the regression equation on the chart. Right? Do you see the regression equation here on the chart?
Yes.
Okay, what's the slope of this regression equation?
Is it 7375?
No, that's not regression. That's not the slope. That's the determination coefficient.
Is it 1.1572?
Yeah, that's the slope. That's the slope.
Okay. So it's not acceleration. So I thought that was the A when you replace the X.
Yeah, that's right. You can put the A here. Huh? Replace here. X with A. Right?
So it's meter per second square, no?
The acceleration is meter per second square. Yes.
Okay.
Acceleration is.
Let me type that. Oh,
2, 3. Like that. Subscript. You go. Like that. Okay. You go. Any more questions?
oh yeah, I have one more question.
Hmm.
So I was like studying alone and
Uh-huh.
like reviewing the lectures and everything. So like it's about Newton's law too. I mean like one that we just did, which is like G value 6.64 times 10 to the negative 11. That's as same as the I mean, what is that value exactly? Like is that 9.8? What's the difference between like 9.8 gravity
Okay,
values?
okay. Lowercase g is an acceleration.
Okay. Oh, okay,
Okay.
right. That's right.
Lowercase is one thing. Lowercase g is one thing. Uppercase g is something else completely different.
Mm-hmm.
We call that it's not an acceleration. It's not a force. It's something else. It's a universal constant.
Uh-huh.
Okay,
Universal.
so those are unrelated factors. Okay, this lowercase g is different from uppercase g. Okay,
So what is uppercase like exactly? Like when I was like reading the textbook, it was like kind of like comparing between like the upper letter and then lower letter. So I thought it was like after you get the G times M sub 1 times M sub 2 over R square is equals to G. That's what I thought, but it's not, right?
Okay, so here you go. We're gonna write that down here. Since you're mentioning gravitational force. Gravitational force of gravity is equal to minus big G, big M, small m, R squared, right?
Yeah, that one is the gravity, the what's that called, the projectile, no?
No, it's not
No?
projectile.
Okay.
It's the universal law of gravity. That's called universal law of gravity.
Okay.
Okay. This
Universal.
G here is different from the other G. Okay. So now there's one more thing. This force is equal to mg, the weight,
Oh, okay.
any altitude. So when you cancel out this m,
Mhm.
you find that big G and small g has this relation between each other. Okay, they're not equals. You see that?
Oh, okay. So when you get rid of the then it's equals or not?
Well, it's not the same thing. Okay,
Not the
this
same
thing
thing.
here, see? Okay, this equation tells us that small g
Mhm.
is different from big G. They're
Oh,
not the
it's
same
this.
thing.
Yeah, but okay, but when after a whole formula like the negative G
Oh,
times M, that's the same G, right? That's lowercase G, no? Yeah, that
lowercase
one.
g is equal to that.
Yeah, right?
Is
Okay.
equal to that. Okay.
Okay, but the lowercase g is not equals to uppercase G
No,
itself.
it's not.
Right, right. Okay.
It's not.
Oh, okay. Okay,
Okay.
now I get it. Let me see. I think I have like a couple more questions to ask you before I go. It's just simple question.
Uh-huh.
Oh, let me see. I think I will just open the textbook. Oh, okay. If this one is Newton's third of motion. So when this, let's say, aircraft is like going forward, right? Is from textbook, and you can see these problems on chapter 4.7.
Is that
example 4.
homework?
It's not homework, it's just a reading part. I was just like reading this and then I couldn't really understand.
Is that in the textbook? Where is it? What is this thing?
Yeah, textbook for it's chapter 4.5. Newton's third law of motion.
Okay. .5.
Yes.
Five. 4.5 Newton's third law of motion. Okay. Is that an example? What's that?
Yeah, it's from the example, I think. So
Which example?
example 4.
Okay. Okay.
Yeah, that one. Yes. So I don't get why okay, so the first part I got it, right, right? But the second part I didn't expect that I need to get that kind of value, because like I thought this would be like just math, like both math subtraction over force problem. You know, when you do that, you get like the one of the values from the solutions. But I didn't know like you have to like do the negative force over mass and stuff. So why do I need to get these two values instead of just like subtracting the both mass and then divided by the force?
Okay. Let me see. Yeah. Okay. There's a mistake here. Okay.
Oh, there's a mistake? Oh,
Yeah. This negative number. This is a mistake here. Okay. Let me see. Let me see. Oh no, it's not a mistake. Sorry, it's not a mistake. Okay. The way we do it, the way I will do it, this example is the following. Yeah, okay. Oh, 4.5. Let's go back there. Nope.
oh,
Yeah, okay, so there is no problem, there is no mistake here. The way I would do it would be like that. Okay. Force, okay. Astronaut is going to be 1, okay?
Okay.
Spaceship is going to be 2, okay?
Okay.
Force, and I'm gonna put the vectorial format
Mm-hmm.
that astronaut exerts on the spaceship, okay?
Mm-hmm.
Is going to be plus 36 newtons in the x direction, okay?
Mm-hmm.
Now, according to Newton's third law of motion, right?
Mm-hmm.
F, and by the way, the book is calling that P.
Mm-hmm.
That's what the
Okay.
book is calling. Okay?
Mm-hmm.
According to Newton's third law of motion, F1 of 2 is equal to minus F, F2 applied to 1, right?
Mm-hmm.
Which is minus 36 newtons in the x hat direction. Okay?
Okay.
Okay, so that was your question, right?
Yeah, but the thing is, like, when you try to get the acceleration for both spaceship and astronaut,
Okay.
how come they're not equal? Because like,
Oh, they're not equal because their masses are different. The spaceship is much heavier than the astronaut, has much more mass than the astronaut. That's why.
so
Okay.
force is always equals, but the accelerations are the difference, right? When it comes to this kind of problem.
Yeah, that's right. In the case of Newton's third law, yes. When two objects interact, yes, that's right. Force, let's see, of 1 applied to 2 is going to be what? Mass of 2 times acceleration of 2. Okay?
Okay.
Okay? Because, okay, F1, okay, and here should be plus, right?
Mm-hmm.
And now, here you go. F of 2 applied to 1 is mass of 1 times acceleration of 2, or acceleration of 1. And this net force is going to be minus 36 newtons. Then you have those two equations.
So how do you determine the negative or the plus? Is it depends on the quadrant or
Well, it depends on that here. See that? You know, the net, let me write in another way. I'm going to write down in another way. The net, first let's put the vector. The net force applied to 2, is just that the force that the astronaut is applying to the spaceship. Okay?
Oh, okay.
All right. And the net force applied to 2 is going to be the mass of 2 times the acceleration of 2. Same thing here, right? The net force applied to 1,
Mm-hmm.
right, is the force that the spaceship is applying to 1. And it's m1 times a1.
Oh, okay.
Okay? That was given by the problem. This one was given by the problem, right? This one here, you obtain from Newton's third law of motion.
Right. Action
Okay?
reaction.
Okay?
But if there's no like given direction or anything like that, and you just have to solve these kind of problems by looking at the picture, do you just have to assume that left side will be the negative side and the right side will be the positive side?
Yeah.
Oh, okay.
Yeah. Yeah.
Oh, okay. Oh, I am. Before I go, I have one more question. So when you draw the free diagram, right?
Free body diagram.
Yeah, free body diagram. Like let's say there's like a right triangle, right? How do you draw that in free body diagram with, let's say there's like two tensions on the two other side. I mean, yeah, like two upper sides and bottom side there's like a mass, like, or the weight. Do you have to just like draw a circle in the middle and then just draw the like line, like a three separated line or
Well,
something?
it goes from problem to problem. Okay, depend on the problem. Depend on the problem that you're talking about. Okay. So which problem, do you have a specific problem that you want me to review that with you?
Yeah, I have I draw this just draw this triangle and I can share it with you. Give me a
Okay.
second. I mean, sometimes like I know that I learned this from the lessons and everything, but